Okay, so now we've got Archie in his submarine, broken down. He's getting it towed by this balloon, and everything's underwater. So it first asks us to draw a free body diagram for the balloon. And it says you can ignore the gravitational force on the balloon since its mass is quite small. So if we look at this balloon, what contact forces do we have acting on it? Well, we have the tension in the string that's touching the balloon. So there should be a force of tension down. The balloon is surrounded by water, which is exerting a buoyant force on the balloon. So we should have a buoyant force up. And then the only other force that could be acting here is the long-range force of gravity, but we were told to ignore that. So that's our whole free body diagram for the balloon. So how about for the submarine? So for the submarine, we have a bit more going on. So we have some contact forces. So the submarine is in contact with the floor. So there's going to be a normal force from the ground. There is a rope attached to the submarine, so there's going to be a tension pulling it to the right. We were told there was friction between it and the seafloor, so there's going to be a force of friction against the way the submarine's trying to move. We have long-range force of gravity acting on the submarine. And last but not least, the submarine is underwater just like the balloon is, so it also has to have a buoyant force. So there's another buoyant force that points up on the submarine. Okay. So I'll put that over here. So it says the submarine starts from rest. What is the minimum balloon volume needed to get the submarine moving? So what's going to get the submarine to move? Well, if you look at the free body diagram for the submarine, and we look in this direction, in order to get the submarine to accelerate to the right, the tension force has to be bigger than the force of friction. Because if we want it to move, the sum of the forces, if we want to move in X direction, the sum of the forces in the X direction has to be greater than 0. So the point at which it just starts to move, the sum of the forces are going to be exactly equal to 0. Okay, so the tension force needs to overcome the force of static friction. So the sum of the forces in X is 0. So we have the tension minus the force of static friction, because it hasn't moved yet, has to be equal to 0. So that tells us that T is equal to F mu S. Okay, so what's the tension in the string? Well, before anything is moving, the tension in this string is equal to the tension in this string. So if we figure out the tension force on the balloon, we can use that in our equation for the submarine. So for the balloon, if the balloon is in static equilibrium, so it hasn't moved yet, we know from our free body diagram the buoyant force on the balloon has to be equal to the... Oops! I just realized I wrote Fg here instead of tension. Very silly. Okay. So the tension points straight down. Okay, so that means that the buoyant force is equal to the tension in the string. And the buoyant force is the density of the water times the volume of the balloon, because the whole balloon is underwater. So this is the weight of the water displaced by the balloon. And we multiply that by G, and that gives us T. So this is the tension in the string. And we can use that in our equation over here for the submarine. So we'll take that and substitute it in here. So rho H2O V balloon times G equals F mu S. And F mu S, I guess we could plug that in. We know that that's going to be mu static times the normal force. Okay, so what's the normal force? If we look back at this picture, to get the normal force, remember it's not just the weight. We have to sum the forces in y and set them equal to 0. So we should have Fn plus the buoyant force on the sub minus Fg sub is 0. So the normal force is Fg minus F buoyant force of the submarine. So let's substitute that in here for the normal force. So rho water, volume balloon times G is mu S times this. So Fg, so that's the mass of the submarine times G minus the buoyant force of the submarine. So the buoyant force of the submarine is the density of the water that it displaced times the volume of the water it displaced, which is the same as the volume of the sub, times G. Now the mass of the submarine here, we can rewrite the mass of the submarine, which we weren't given, but we were given the submarine's density. So the mass of the submarine divided by its volume is its density, which means that ms is the density of the sub times the volume of the sub. I'm going to pull the G out of this. So that'll be rho sub V sub minus rho H2O V sub. And now all we have to do is solve for the balloon volume. So we just have to divide both sides by rho H2O times G. And you could pull the volume of the submarine out over here. So you would get the volume of the balloon is this G will cancel with this G. The volume of the balloon is mu S times rho submarine minus rho H2O times the volume of the sub divided by rho H2O. And that's it. Okay. So to find the acceleration of the submarine after it starts moving with a balloon, what's going to change? So instead of the net force being equal to 0, like we used here, the net force in this case is the mass of the submarine times the acceleration of the submarine. And this is what we're trying to find. Now, the only thing that's going to change in the forces here is that instead of kinetic friction, or instead of static friction, we're going to have kinetic friction. And that's the major change. So if you make that major change appropriately, this has a little bit of algebra. I'm not going to go through it here. You can see the full solutions if you want to do that algebra. But basically, if you write down the main forces that are acting, you would get full credit on that problem. Let's see. We only have one more.